So when we have a regular shape and we know its formula, that's obviously the easiest way of finding the area under the curve. When we have these irregular shapes and we know the function of the curve, we can integrate them. But of course there's some functions that we can't integrate. Certainly at this stage we haven't learned how to do trig or log functions or all sorts of things. So we need a way of approximating. Originally we used rectangles, but they weren't real good because the rectangle had a lot of over, estimates. Rather than a rectangle though, if we do a trapezium, then we're going to cut that over estimate quite a bit. So I simply draw in the other side, join up the point where function A meets function B, and I get a trapezium. Certainly that's going to be a better estimate than the rectangle. Okay, we've cut out that triangle if you like. So we could work out with formula of a trapezium. Remember it's half height, which in this case would be B minus A, sum of the parallel sides, so function A plus function B. And that would give us an estimate. But just like we saw with the rectangles, the more trapeziums we have, the better the estimate. By just creating one more trapezium, so I'll put C in the middle, you can see, well, and trust me, it is the same curve, I haven't done anything dodgy there, that the actual overestimate has cut down quite a bit by just adding one more trapezium. And so for this one, it'll be the two trapeziums added together. But we can simplify this formula a bit. Because I've placed C in the middle, I know that C minus A is the same as B minus C. So we have a common factor here. Even though one of them says C minus A on 2 and the other one says B minus C on 2, they are in fact the same value. So I could factorise that out. I've chosen C minus A on 2. It doesn't really matter which one I write. But then in the braces here, I'm left with function A, twice function C, and function B. All right, well, let's now turn it into three trapeziums, or trapezoids, as you sometimes hear the Americans say. So again, I've made sure they're equally spaced. So C minus A would be the same as D minus C, would be the same as B minus D. So if I was to factorise that one, and we start seeing a pattern emerging. Whenever we do it, we've got one lot of the end ones, because they're only included in one of the trapeziums, but we always get twice the function values of the ones in the middle, because they're involved in two trapeziums. So I can generalise that to a formula then. Well, sort of a formula. We know the exact area would be the integral from A to B. Okay? And if we can integrate it, terrific, we get our exact answer. But otherwise, I can use this sort of formula. H on 2, so the height of our trapezium, whatever that common height is, I'm saying the first one I'm calling y0 and the last one yn. Some textbooks you'll see them start at y1 and then the last one becomes yn plus 1. Okay? I like to finish on n, so I start with y0. And then how to write the middle bit, I just went, 2y the others. So all the ones in the middle. To work out the height then, I could always go, well, it's B minus A divided by the number of trapeziums or strips. Sometimes you'll see them called, or sometimes you'll see them called intervals, but basically how many we're breaking it up into. And you're always going to end up with one more function value than you do the number of strips. So be careful with that. Sometimes in a question they'll say using so many function values. Other times they'll say using 5 strips or 5 trapeziums. It's important because when you work out H, B minus A over N is the number of strips or the number of trapeziums. So if they say using 5, for instance, function values, then I know I've got to divide by 4 because there'll always be one less strip than the number of function values. Okay, let's do something that I can work the exact value out for, but I can't actually integrate yet. So 4 minus x squared to the power of a half, which is a semicircle. So we could work out the exact area. We just don't know how to integrate this one yet. We're going to go between 0 and 2. So the height, we're using 4 intervals. So 2 divided by 4, we're going to place them a half, every half. I like to draw up a table of values. I think it makes life a lot easier. And so we're going up by halves. I'm starting at 0, then 0.5, then 1, then 1.5, then 2. Summing into the y. They said 3 decimal points. You'll notice my table of values is 4 decimal points. I always like to carry one extra until the last line, in case there's some sort of rounding error in there. So I carry one extra decimal point of accuracy, and then I can be pretty sure that my rounded off answer at the end will be okay. There's the dodgy little formula, h on 2, y naught, 2y the other ones, and yn being the last one. Another way of remembering it is simply doing this. On the top of the table of values, I remember, okay, it's 1 times the n ones and 2 times all the ones in the middle. And that just reminds myself, okay, these ones, the function value I'm multiplying by 1, these ones I'm multiplying by 2. So I just go, okay, 1, 2, 2, 2. So let's sub in 0.5 over 2. So the end one is 2, and at the other end, 0. And then 2 times all the ones in the middle. And rounding off that answer to 3 decimal places, I get 2.996. So how good is that? Well, the actual area turns out to be pi. Because we're talking about a quarter of a circle. We're going from 0 to 2. The radius is 2, so it's a quarter pi r squared, quarter of 4 pi. Pi would be the exact value, so 3.1415926533527950288419 approximately. How much is the error? How much is the error? Okay, so the exact value, 3.142. We came up with 2.996. So the difference between the two would be the actual error. Working it out as a percentage, so dividing by the exact amount times by 100, 4.6% is about the error. There's another way, which actually is more efficient, and that's Simpson's rule. And what Simpson's rule does, it actually estimates the area using parabolas. So it's estimating the area under a curve with a curve. So we get a much better estimate. So again, the exact area would be from function x, from a to b of function x. Formula is very similar, but instead of being 2 times all the ones in the middle, it's 4 times what I call the odd ones. That's if I start off with calling the first one 0. So then y1, y3, y5 would be the odd ones, and 2 times all the even ones, so y2 and so on. If you're looking at a textbook that starts with y1, then theirs will be the other way around. Because I'm starting with 0, so the first one after that becomes an odd one, y1, whereas if they're starting with 1, first one after that would be y2, so it'll be an even one. Height's still the same, still work that out the same. So let's do the same question and see how much of a better estimate. So there was our table of values. But this time I'm going to use Simpson's rule. So it'll be 1 times the n ones. Basically 4, 2, 4, 2, 4, 2, 4, 2. So start with a 4 to the middle. Notice the symmetry there. This is the thing about Simpson's rule. It works very well when it's symmetric like that, 1, 4, 2, 4, 1. If I was to have one more function value, it wouldn't be as good because you wouldn't have that symmetry. Because basically what Simpson's rule does, it uses parabolas, but it combines a concave up parabola with a concave down parabola, so you sort of need it in pairs. And so you end up with an odd number of function values to be a good estimate. That doesn't mean you can't use it with an even number of function values, but it just won't give as good an estimate as if you had one. All right, let's sub into it then. 0.5 on 3, 2, 0, they're the end ones, 4 times the odd ones, so y1 and y3, and 2 times the even one, the one in the middle, 3.084, certainly a lot closer to pi. And in fact, that estimate turns out to be 1.8%. An alternative way of working this out, I saw this once in a solutions, I think it was on the border study side, I think it was their solutions to an HSC one year. And it was just their working out. They didn't explain what they did. They just had their working out. I thought, what on earth are they doing there? Why does this work? And once I finally worked out what they were doing, I said, oh, okay, I see. So, all right, there's our table of values. They then said, right, there's the area. Bang. What have they done? On the top, it's still the same as what I had in my formula. End ones, and then 2 times, and this is trapezoidal, so 2 times all the ones in the middle. But on the bottom, all those numbers added together. So the 1 plus the 2 plus the 2 plus the 2 plus the 1, and then they multiply it by the overall height, so b minus a, so 2 minus 0 in this case. And trust me, when you put that into your calculator, you do come up with the same answer of 2.996. It also works for Simpson's rule. So the example I saw was just on the trapezoidal rule, but I thought, well, surely if it works for one, it should work for the other. So this was our table of value for Simpson's rule. So using the same idea, on the top of the fraction, we'd have the same as I put in the parentheses, so 2 and 0 are the end ones, 4 times the odd, 2 the even. On the bottom, there's the pattern, but added together. 1 plus 4 plus 2 plus 4 plus 1. Again, times it by the b minus a. And sure enough, if you plug that into your calculator, we get the same answer. So it's just a different way, I guess, of setting it out. It's not too bad. Ooh, 11 over the odds, 11J the evens.